Okay, so in chapter 4.4, we're going to go over another type of function called rational functions. So we've already gone through polynomial functions. And the only rational function, well, just like a rational number is just a fraction, a rational function is just a fraction of two polynomials. So here's an example. K of x equal to 2x cubed plus 5x minus 1. That's a polynomial, perfectly good polynomial. And then I'm going to put it over x cubed minus 7x plus 6. So it's just a fraction of two polynomials, and and if I do have a fraction of two polynomials, then I have a rational function. All right, well, let's talk about domain. Again, domain is what x is, or what inputs can you put into the function. And remember, the domain for polynomials is all real numbers because there's nowhere in a polynomial that's going to be undefined. But since this is a fraction, we have to be careful about the denominator. There could be x's that we put into the bottom, and we get 0 on the bottom, which means we're going to divide by 0, and that's going to be a problem. So to find the domain for our function, if it's a rational function, we need to check and see what are the zeros of the denominator. And the domain will be all real numbers that aren't zeros of the denominator. So let's look at an example. So another rational function, r of x equal x squared plus 4 over x squared minus 2x minus 8. What is the domain? Go ahead and pause and ask yourself, what is the domain? Right, so the domain is going to be every x, all real numbers for x, except where the denominator could be 0. So the easiest way to find where the denominator is 0 is if you can factor, that's going to be the best way. Because remember, that's how we found zeros before, was by factoring. So luckily, this one factors into x minus 4 times x plus 2, not too difficult. And we see that that's going to be 0 when x is 4 and when x is negative 2. So our domain is going to be all real numbers except when x is 4 and when x is, and we get that from that factor, that first factor, and the other value that's not in the domain where the function would be undefined is at negative 2, and we get that from the blue factor there. Okay, so another feature of rational functions that might help us in terms of graphing is going to be the intercepts. So let's look at the y-intercept first, because there's only going to be one of those. And the y-intercept is going to be the point where you put in 0 for the input and what comes out. So like if I just draw this isn't a rational function that I just drew some random polynomial, but you get the idea. The y-intercept is where it crosses the y-axis, and so that's going to be when you put x is 0, what comes out, and that's going to be your y-intercept point. Okay, the x-intercept, now there could be more than one, because the x-intercept is going to be when the output is 0. The x-intercept is going to be the zeros of the function, and since it's a fraction, then we know the only way the fraction is going to be 0 is if the top is 0. So the x-intercepts are going to be where the numerator is 0, but is not a 0 in the denominator, because if the 0 is in the denominator, then it's undefined. So, okay, let's look at an example of finding some intercepts. So let's just look at a rational function here. So we'll look at finding the intercepts for f of x equal to x squared minus x minus 6 over x minus 2. Okay, so let's just start with the y-intercept because that's often the easier of the two. So for the y-intercept, all we got to do is put in 0 for the x and see what comes out. So, okay, great. So f of 0, what is that? Well, 0 squared minus 0 minus 6 over 0 minus 2, which is going to be just minus 6 over minus 2, which is going to reduce down to 3. So the y-intercept is going to be the point 0, 3. because we put in 0 for the x and we got 3 out for the f, the output. All right, let's get the x-intercepts. So again, for the x-intercepts, it's going to be where the function is 0, where 0 comes out, right? Because that's where it's going to cross the x-axis, is when the output is 0. And this fraction is going to be 0 when the top is 0. So we can just focus on the top, the x squared minus x minus 6, set it equal to 0, and find the zeros. So that's going to factor pretty nicely into x minus 3 and x plus 2. And we get 2 zeros there. We get zeros at x equal to 3 and at x equal to, so we get one of the zeros, x equal to 3. It's going to come from that factor. And you kind of see where this built on from the earlier sections where we were finding zeros of polynomials. And the other 0 is at negative 2. And we just quickly check and make sure that those aren't zeros of the bottom, like that you don't plug those in for x and you get 0 on the bottom, because that would be a problem, but you don't. Both of those, 3 on the bottom, x minus 2. So if you put in 3, 3 minus 2 is 1, that's not 0. And minus 2 is minus 4, so that's okay. So we have our two x-intercepts, 3, 0, and minus 2, 0. And we can put those intercepts on our graph. Okay, so the next feature of rational functions that we're going to look at, we're going to go through all the features of rational functions that are important in terms of being able to sketch a graph, and then at the end I'll do a complete example sketching a graph. So this idea of continuity, and remember this because this is going to come back in the early part of calculus, okay? This idea of what it means to be continuous or to have continuity. But we're just going to kind of introduce the idea of it here with rational functions. So what does it mean for the graph to have continuity or to be continuous? Well, the rational functions are going to have breaks in them because of having a denominator that can be undefined. So with a rational function, you're going to have a break wherever it's not defined. And there's going to be two kinds of breaks that we're going to look at. One is going to be vertical asymptote, and the other is going to be a hole. So we'll look at an example of each of those. Just remember that on polynomials, there was no places where the polynomial function was undefined, so we didn't have to worry about continuity with polynomial functions. All right, so the first kind of break we're going to look at is a vertical asymptote. And you're going to get that where you have a 0 on the denominator or the bottom of your fraction function or rational function. And so you have a 0 in the denominator, but it's not a 0 in the numerator. The idea being, it'll be easier to see with an example. If the 0 is in the denominator and the numerator, that means you have a factor, the same factor on top and bottom that will cancel out. And in that case, you're going to have a hole, but we'll get to that in the second example. Okay, so we're going to find the vertical asymptote for this rational function. Okay, so we're going to find the vertical asymptote, and we're going to sketch the graph for this. Okay. Because all this that we're going over is information that helps you sketch the graph, essentially. Right. So we're going to sketch the graph near the vertical asymptote once we found it. So we got a rational function, f of x equal to x plus 2 over 3x minus 9. Well, again, the breaks are going to be where it's undefined. And a fraction's undefined when it's 0 in the denominator. So we just focus on that denominator and say, hey, is there any x's where that can be 0? Well, yeah, because if I factor it, I mean, you don't even really need to factor it to see it, but yeah, might as well. Then 3x minus 9 could be 0 when x is 3. And so we just check and say, okay, 3 is a 0 of the denominator, and if we put it into the top, it's not 0. So it's not going to cancel out. So we just check in the numerator real quick, make sure that 3 is not a 0 in the numerator. And since it's not, it means we're going to have a vertical asymptote at x equal to 3. So what that's going to look like is on our graph, we're going to just, at x equal to 3, we're going to draw a dashed vertical line to tell the person that's looking at our graph, hey man or woman, this function's not defined at x equal to 3. There's a break in it, right? Okay, now how do we know what the function looks like around this dashed vertical line, right, where it's undefined? Well, there's a lot of ways to do this, but the thing I suggest is just put a x just a little bit to the left of 3 and a little bit to the right, and just see if it's positive or negative. And that'll tell you how it's going to approach this dashed vertical line. So for example, if I want to look at to the left of 3, I know I already drew it without showing you why I did that, so I'm going to explain now why I drew it the way I did. So when x is, we got to choose something like close to 3 on the left. Let's say like 2.99, right? We just need to know if the graph is going to be positive infinity or negative infinity, because it's always going to be just one of those two options around the vertical asymptote. So if we put 2.99, okay, we get like 5 on top roughly, and we get basically 2.99 minus 3 is going to be like a really small negative number. And if you divide by a small negative number, try it. Put in your calculator. Just do like 5 divided by negative 0.00000001. What you're going to find is that's going to be negative infinity. When you divide by a very small number, you get a very big number. Like 1 over 0.00000001 is like a billion, right? So since it's negative infinity, I know the graph is going to approach towards negative infinity on the left side of that asymptote. And then on the right side, I'll just check like 3.01 and I get positive infinity. Okay, so I promised you that there was two kind of breaks, right? So we went through the vertical asymptotes, and there's another kind of break. It's important to keep in mind that the breaks, they always occur when there's a 0 in the denominator. Okay, that's just something to keep in mind, because that's where that's where the rational function or fraction function is going to be undefined when the bottom is 0. So that's always where you're going to have the break. It's just that in the first case example we did, 3 was a 0 on the bottom, but not on the top. So it's a vertical asymptote, that dashed vertical line. You have a hole where, let's say you have a number C. I don't know why I chose C, but there's a number C that's a 0 of the bottom, the denominator, as well as the top, the numerator. Okay, so basically this number you put in, you get 0 on the bottom and you get 0 on the top. What happens is that means that those two factors kind of cancel each other out. So you're not going to have like positive or negative infinity. You're just going to have a 0. Not a 0. You're going to have a hole in the graph where that is. So let's look at an example. F of x equal to x squared minus 9 over x minus 3. Now, before we even knew if this is a hole or vertical asymptote, we ask ourselves, where's the break going to be? Well, it's going to be where the bottom is 0, and that's going to be where x equal to 3. But now we're going to look at, okay, wait, does 3 give me 0 on the top as well? Well, it does, right? Because the top is x squared minus 9. Its difference of squares. It can be factored to x minus 3 times x plus 3. And the x minus 3 factors are going to cancel each other out. And so since 3 is a 0 of both the bottom and the top, then you have a hole. And when you have a hole, the easiest way to graph it is going to be to cancel the factors that are the zeros on top and bottom. So in this case, I'm going to cancel the x minus 3 on top and bottom. And you're left with just x plus 3. And that is going to be what the graph looks like everywhere except for the hole. And x plus 3 is pretty easy to graph. It's just a line, right? So I just need 2 points. Let's just pick when x is 0, what comes out? 3. Okay, so there's 1 point. And if I put in, let's just get the x-intercept. So that's 0 when x is negative 3. So the point negative 3, 0 is on the line. Great, I have 2 points. That's all I need to sketch the graph of the line. But one thing I'm going to do is I'm going to put the hole in here. The hole is at x equal to 3. And if you want to know where the whole point should be, you put it into the function that you've canceled out. So that x plus 3, and I get 6. And so the hole is going to be at 3, 6. I draw the hole there, and then I just sketch the graph. So it's important to keep in mind with the holes is that they can occur when you have a 0 in both the denominator and numerator. But even if you have a 0 in both the bottom and top, it still could be a vertical asymptote. It might not be a hole. So this example will hopefully make that clear, where you just want to be a little bit careful. So here I have the function f of x equal to x minus 3 over x squared minus 6x plus 9. And I'm supposed to find any holes or vertical asymptotes. So maybe pause and ask yourself, how am I going to find these breaks, right? What am I going to do to find the breaks in the graph? Where are those going to be? And if you said to yourself, well, it's going to be where the 0 is in the denominator, then you would be correct. Good job. So what we're going to do is we're going to take the bottom denominator, we're going to factor it, and find the zeros. Well, it factors into x minus 3 times x minus 3, so we have a 0 at x equal to 3. And 3 is a 0 on the bottom, and it's a 0 on the top. So we might say, oh, wait, that's going to be a hole, right? Well, no, because when you cancel out those factors, you're left with 1 over x minus 3, and 3, when you plug it into this, is going to be still 0 on the bottom, and 1 divided by 0 is going to be undefined. So it's not a hole at 3, even though it was a 0 of both the bottom and top. The idea is that because after you canceled out the factor on the top and bottom, but it's still 0 on the bottom when you plug in 3, it's going to be a vertical asymptote. So we know it's a vertical asymptote because you have, some number divided by 0, so it's going to be undefined at 3. So we put the vertical dashed line at x equal to 3, and if we want to know how the graph is going to, remember, the graph can either go to negative infinity or to positive infinity. And if we test something to the left, like 2.99, well, 1 over 2.99 minus 3 is going to be 1 over a really, really, really small negative number, which is going to be a really, really big negative number. And similarly, we could test on the right side, like 3.01, and get that the graph is going to go to positive infinity. So we've talked about domain, the intercepts, and the breaks. And the breaks could either be vertical asymptotes or holes. So there's one more feature about, especially as it pertains to rational functions, and that's the end behavior. And after that, you have everything you need to really sketch good graphs of these. So what's the end behavior of rational functions? Well, what are the ends of the graph? Well, if you think about it, if you go down to the far right end, x is very, very large, basically goes to infinity. And the other end, on the left end, x goes to very, very large negative infinity. So when you want to find the end behavior for the rational functions, you're just you're going to plug in x as a very large number and a very negative number and see what happens. So let's look at this. We're going to look at this example. We're going to find vertical asymptotes, just as a review from earlier, and we're also going to look at the end behavior of this function, this rational function. Okay, so our rational function is going to be f of x equal to negative 4x plus 8 over 2 minus 3x. Okay, so ask yourself how you would find the vertical asymptote. Right, you want to do where it's the vertical asymptote, or any break, is going to be where it's undefined, and that's going to be where the bottom is 0. So we just set 2 minus 3x equal to 0, and we see that's going to be 0 when x is 2/3. So we have a vertical asymptote at x equal to 2/3, because again, that's where the bottom is 0. And well, we check and make sure it's not a 0 on the top, and if you put 2/3 on the top, you're not going to get 0. So, okay, now the end behavior. I'm going to introduce some notation that's going to be some calculus notation, okay? But I just want you to start getting used to it now. The idea of a limit, what I'm writing here is I'm basically saying, hey, x and then arrow to infinity, and I'm basically saying, hey, x is going to go to infinity, okay? And what's going to happen to this thing that I'm going to write? Well, if you think about it, when x is infinity, does it care about plus 8? No, it's like a little, mosquito, a Jung that it's going to swat off. And same thing with the bottom, minus 3x, well, plus 2, it doesn't care about infinity doesn't care about the plus 2. So you can basically cross those out, and then you get minus 4x over minus 3x, and the x's cancel, and you get 4/3. So what this is saying is that, hey, when x is really, really big, the graph is going to approach 4/3. And the same thing from negative infinity. Again, negative infinity doesn't care about plus 8 and plus 2, so those can be crossed out. And you get minus 4x over minus 3x, and it cancels to 4/3. So what this means is the graph is going to approach 4/3 from both ends. And I mean, by the ends, I mean like towards positive infinity on the x and negative infinity. So that's going to be a horizontal asymptote, as you may have heard before. And so we're just going to sketch that in there, that horizontal line at y equal to 4/3. And the graph is going to basically approach that line. It's going to be like a guideline for the graph at the ends, at negative infinity and positive infinity. So what I'm going to do from here is to sketch the graph, I just need to know how the graph approaches the vertical asymptote. So I'll just look at it from the left side. Okay, if something is like a little bit less than 2/3, say 0, because like I don't want to plug in 1/3, it's like too hard for me. So if I put in 0, I just need to know if it's going to be positive or negative, and that's going to tell me if it's going to go to negative infinity or positive infinity. And if I look at putting in 0, I'm going to get positive on the top and bottom, so the whole thing is going to be positive. So it goes to positive infinity. And then on the right side of the vertical asymptote, I see that when x is 1, for example, I get a positive on top but negative on the bottom. So it's going to go to negative infinity. And then on either end, it's going to follow the horizontal asymptote. Okay, so we'll do one more example of end behavior. And this end behavior happened to be a horizontal asymptote. And you're going to find you'll get that when the degree of the top and the bottom is the same. So in that last example, they were both degree 1 on the top and bottom. When the polynomials on the top and bottom are the same degree, it's going to be a horizontal asymptote. When the degree is not the same, then you get different kinds of end behavior. And so here's an example. F of x equal to x squared minus x minus 6 over x plus 4. We need to sketch the graph for this. Okay, well, let's just find any vertical asymptotes or holes first. Is there anywhere where this is undefined? And where are we going to find the breaks? Exactly, where the bottom is 0. And the bottom is 0 when x is equal to negative 4. And we quickly look at the top and see, well, it's not going to be a 0 on the top, so we're going to have a vertical asymptote at negative 4. So we'll go ahead and sketch that in. It's a dotted vertical line at x equal to negative 4. Great, so that gives us our breaks. Now, I can't remember if I sketched it around negative 4 or I went for the end behavior. I probably tried to figure out if it was going to positive or negative infinity, right? Hopefully you did that, Eric. Yes, you did. Okay, so you put in something to the left of negative 4, like negative 5. And again, you only need to know the sign. Don't bother finding the exact number. It's not important. It's just either positive or negative infinity. So if I put in negative 5, my factors are negative 5 minus 3 is negative, times negative 5 plus 2 is negative, over negative 5 plus 4 is negative. So negative times negative is positive, divided by negative, negative. So I know the graph's going to go to negative infinity from the left side of that vertical asymptote. And plug in just the easiest thing you can on the right side, maybe like negative 3, and you're going to see that you're going to have two negatives on the top divided by a positive, so overall you're positive. So the graph is going to approach positive infinity from the right side. Okay. And I recommend you do that whenever you sketch your vertical asymptote. Just test an x on either side so you know if it's going to positive or negative infinity. And don't waste your time finding the exact number, just if it's positive or negative. Okay, now for the end behavior, we're going to look at, again, using this calculus notation that's going to come up a lot more when we get to the calculus part of the course. the end behavior says, hey, what happens when x goes to infinity? What happens to this function? So the way we write that is limit as x goes to infinity with the arrow, x squared minus x minus 6 over x plus 4. Well, one thing is we can cancel out x squared minus x minus 6. It doesn't really care about, x squared doesn't care about x and 6. It's a lot bigger than those when x is infinity, so you can kind of scratch those out. And on the bottom, infinity doesn't care about plus 4. So if you scratch that out, you get x squared over x, which is going to reduce down to x. So the graph is going to go to infinity. So you might ask yourself, can we really draw some type of end behavior? Well, we can, and the idea is we're going to rewrite this in a way where it's easier to see what that is. So we're actually going to do the division. So we're going to divide x plus 4 into x squared minus x minus 6. So I'm doing the long division here. And when I do the division, I get x minus 5 plus some remainder here. Okay, so remainder 14. So the remainder is going to be 14 over x plus 4. Now, let's evaluate that limit again, but use it in this form. It's going to be easier to see what's going to happen to the graph. So I just rewrote it. I rewrote the rational function by doing the division. So I get limit as x goes to infinity, x minus 5 plus 14 over x plus 4. Now when x goes to infinity, that bottom in the remainder part is going to go to 0 because you're going to have 14 over infinity, which is going to be 0. Because like divide by 1,000,000,000 and you'll see that it's going to be 0. So the idea is that at the end, when x is really, really big, the graph is going to follow x minus 5. And we know what x minus 5 is just a slanted line. So that's why it's called a slant asymptote. So we just got to sketch this line. So when x is 0, we just need 2 points. So x is 0, y is negative 5. And when x is 5, the y is 0. So we put those 2 points, we connect them. That gives us our slant asymptote. And if we follow what we know about the vertical asymptote, we're done. We can sketch our rational function. It's going to fit into the guidelines, right? It's going to, at the ends, at the left end, at negative infinity, it's going to follow this slant asymptote that we sketched. And we already figured out it goes towards negative infinity from the left side of the vertical asymptote. And so there you go. You've got a sketched graph for this rational function.